Streaming. Hello and welcome back to Calculus 2, section 610, the last one, chapter 6. So on hyperbolic functions, and this has two parts: the pre-calculus part where we define hyperbolic functions, and then the calculus part where we use them to in conjunction with derivatives and integrals and so on. So the birth of hyperbolic functions happened with Euler, like many other things. He was well aware, because he figured it out, that you can write sine x as e to the x minus ix, minus e to the minus ix over 2I, which is a complex form using exponential functions. And there was one for cosine as well. These are not part of our course in any way. There's no I in the denominator. And obviously these are complex functions. But then Euler said, what would happen if I am to remove I? If I am to remove the complex part and just write e to the x minus e to the minus x over 2. And what would happen if we had the same thing with the plus? And then he worked out all of these combinations in algebra in his head, because for most of his life he was blind. He was dictating all of this mathematics to scribes. And the properties of these functions turned out to be very similar. I said properties of these functions turned out to be very similar to trigonometric properties. Yet these functions are nothing like trig functions. So he decided to call them hyperbolic functions and then use the sine hyperbolic x, cosine hyperbolic x, and these are the definitions, the two that you absolutely must know so you can do technically anything else. Now, the interesting part is that the properties are similar, but these functions are nothing like trig. You have to understand and remember that trig are periodic functions. They repeat on a cycle. You wait 2 pi and then the sine wave repeats. And then at 4 pi it repeats again. And a 6 pi and so on. And a cosine does the same thing, and a tangent every pi. These functions are not periodic at all. So fundamentally they are much different. These functions are much closer to x squared and x cubed and all of those functions, the polynomials, than they are to trig. But the properties of these functions are very close to trig, so the name fits. And we also have the other 4, the hyperbolic tangent, which is the division. So tangent hyperbolic x is sine hyperbolic x over cosine hyperbolic x, which eventually is e to the x minus e to the minus x over e to the x plus e to the minus x. And you have the others, the cotangent hyperbolic x, which is cosine hyperbolic x over sine hyperbolic x, which is e to the x plus e to the minus x over e to the x minus e to the minus x. Secant hyperbolic x is 1 over cosine hyperbolic x, which works out to be 2 divided by e to the x plus e to the minus x. And a cosecant hyperbolic x is 1 over sine hyperbolic x, which is 2 over e to the x minus e to the minus x. Cosine hyperbolic x is very important for electrical engineering because the cables that you see, right, the power towers that you have, and you stretch the wire in between the cable that will carry the high voltage, all of those are modeled through cosine hyperbolic. So it's a very important function. And there are many other applications. You are going to use some of these functions in your differential equations class. So you will see that certain equations will have trig as a solution. Certain equations will have hyperbolic functions as a solution. So you will really have to know how to deal with this stuff if you're taking more courses later on. Now, there are properties, and I mentioned before, and the properties are close. So properties of hyperbolic functions remind of what you expect for trig, but they're not the same. So we have you know how sine squared x plus cosine squared is equal to 1?
Yeah.
Well, this one is cosine squared hyperbolic squared minus sine hyperbolic squared equals 1. So it's kind of close. Now you can simply prove all of these formulas if you're interested by replacing these sines and cosines with these and then squaring them and working out the algebra. It should take about a minute for each. We have 1 minus tangent squared, tangent hyperbolic squared x is equal to good old secant hyperbolic squared. It's so close. Cotangent hyperbolic squared minus 1 is the cosecant hyperbolic squared. Then we have the sum of the values. Cosine hyperbolic of x plus y is equal to cosine hyperbolic x cosine hyperbolic y plus sine hyperbolic x sine hyperbolic y, and sine hyperbolic x plus y is equal to sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x sine hyperbolic y. Very close. None of them are exact until we reach the sine of 2x, sine hyperbolic 2x. This one is identical. This is the only one that is identical. All others are off. Now, to make the matters worse over here, for some this will be amazing. Here's your sine squared hyperbolic plus cosine squared hyperbolic. It's not equal to 1. It's equal to cosine 2 hyperbolic. And the power reducing finally. This one is identical. Oh, actually, I should put plus 1. So that the other one makes more sense. Now what's interesting here is to see how these formulas swap places. You see, this formula here is supposed to be 1, right, for trig. And then if you go all the way on the top, this is actually cosine 2x. Because like cosine 2x in trig is cosine squared minus sine squared. So they swap places. And then these are swap the terms. So they are very, very close. But none of these are periodic functions, so we cannot confuse them with trig. Now, usually what I ask on the exam is to derive one of these using the E, and this is the last thing I'm going to do tonight, and we're going to pick up with trig, not trig, the integrals and derivatives, or calculus, tomorrow. So the last thing is I would like to pick any one of these equations and just work it out, which is algebra. So let's do the one of the power reducing, let's say. So prove cosine hyperbolic squared x equals to cosine hyperbolic 2x plus 1 over 2. So you will plug in, on this side is e to the x plus e to the minus x over 2 squared, right, because that's the cosine hyperbolic squared. And that needs to be equal to, on the other side you have e to the x, 2x, sorry, plus e to the minus 2x over 2, everything plus 1 over 2. So these two sides need to be the same once you work all of the algebra out. So let's do it. When you apply the square, you have a square of binomial, you use the formula. I have it on the board, very convenient. So I'm using that formula. It's e to the 2x plus e to the x times e to the minus x, that's e to the 0, which is 1, so it's just 2, plus e to the minus 2x divided by 2. So that's the left-hand side. The right-hand side, we have to work out this 2, so it's going to be e to the 2x plus e to the negative 2x over 4. Oh, I forgot to square 2 on the other side is 4. Plus 1/2. So all I need to do is to add on the right-hand side, and we have the same thing. When I add on the other side, it is common denominator is 4. I get e to the 2x plus e to the minus 2x, and then plus 2 because of the... And you see that the left and right side are the same. So this is how you show that these formulas are valid. Now I encourage you to try at least 2 or 3 other ones at random. All you need to do is to sub what the E definitions are and just work out the algebra. There's nothing else. Tomorrow we are going to finish this section, so it will be a part 2 on hyperbolic functions, and we are going to work out the derivatives and the integrals for hyperbolic functions. The problems are going to be, again, the chain rule, the use sub. We're not learning any new calculus, we're just applying calculus on a new type of a function. So we'll deal with that tomorrow. See you all in 22 hours. Actually, 21 hours and change.